Okay, in last class we have discussed how to represent a polynomial using a linked list. Now the last point of your third module is a representation of sparse matrix using a linked list. You know what is meant by sparse matrix. Sparse matrix is a matrix where we have more number of non-zero terms, more number of zero terms compared to non-zero terms. Now there are two ways in which you can represent a sparse matrix. The first way we have already discussed, that is triplet representation. That is nothing but you are going to use array of structures for representing your sparse matrix, and today we are going to discuss about the second method, that is linked representation. Just have an overview of the first one, then we'll move to the second method for representing a sparse matrix. Now in triplet representation, that is in array representation, you are going to create array of structures to store a sparse matrix. Now this structure is going to contain three members. Those are a row, column and values. Now for example, this is an sparse matrix which I want to represent using a triplet representation, that is nothing but array representation. Now to represent this sparse matrix, I am going to create an array of structures of size 1, 2, 3, 4, 5, 6, 7. This is an array of structure of 7 elements. Now in this array of structure, how the elements are going to be stored? The first, that is array of 0, is going to contain array of zeros. Row is going to contain total number of rows in your matrix. Now the total number of rows are 5. 0, 1, 2, 3, 1, 2, 3, 4, 5, and column is going to contain total number of columns, that is 1, 2, 3, 4, 5, 6. 6 columns you have, and values of a of 0 is going to contain the total number of non-zero terms in your sparse matrix. Now if you can count the total number of non-zero terms, how many non-zero terms are there in this matrix? 1, 2, 3, 4, 5, 6. Now 6 non-zero terms are there, and this a of 0 value is going to contain this value as 6, means it indicates you have 6 non-zero terms in your matrix, and each index is going to contain a non-zero term information. Now the first non-zero term is this 9. Now this value is stored in this index, and its row number is 0 because it is presented so row number 0, and its column number is 4. Similarly, all non-zero terms are going to be stored in this array of structures. This is how you can represent a sparse matrix using array representation, which is also called as triplet representation. Now array, in the sense, you are going to use array of structures. This is how you are going to store a sparse matrix using a array. Now the next second way we are going to discuss today, that is linked representation. Now in linked representation, we are going to use a linked list data structure to represent a sparse matrix. Now in this linked list representation, we are going to use two different types of nodes. One is called as header node, and second one is called element node. Okay, we are going to use two different types of nodes in linked representation of your sparse matrix, header node as well as element node. Now header node is going to contain three different fields. It is going to contain three different fields, and element node is going to contain 5 fields as shown in the figure. Now you can see here header node consisting of 3 fields: index value, down, right, and element node is going to contain 5 fields: row, column, value, down or up, and right. Now for what purpose these fields are used, that we are going to discuss here now. Now the header node, now these nodes are going to be attached at For every row and column, you are going to have a header. For every row and a column, you are going to have the header node. Now this header node is going to contain these three fields: index value, down, and right. Now the index value represents the row number or the column number. Index value is going to represent the row number or the column number. Down is going to contain a pointer to the next non-zero element in your next non-zero element in the same column. Down is going to point at the next non-zero element in the same column, and right is going to contain a pointer to a next non-zero term in the same row. Down is going to contain a pointer to a next non-zero term in the same column, and right is going to contain a pointer to a next non-zero term in a same row. This is about header node, and these header nodes are going to be used for each row and column. You are going to have a header node. Now the next node you are going to have is the element node. Now this element node is, just a second. The element node consists of 5 different components: the row, column, value, down, up, and right. Now the down, up, and right working are same. Down or up is going to point at the next non-zero term in the same column. If you don't have the next non-zero term in the same column, then it is going to point back to the header. Hence it is given as down or up. If you don't have the next non-zero term in the same column, then this down or up is going to point back to the header, and right is going to point at the next non-zero term in the same row. And these are the three new fields which are added in this element node. Now row indicates the row number, column indicates the column number, and value indicates the non-zero value which is present at this row and column number. This is how the linked representation is going to contain two different types of node: header nodes and elements. Now let us take the same example which we have discussed earlier. Now the see here. Now consider this sparse matrix. Now if I want to represent this sparse matrix in terms of linked list representation, just a second. Okay. Then for each row we are going to have the header nodes. Now here I will have header node for this row: H1, HR1, HR2, HR3, HR4, HR5. Similarly, for each column also I am going to have header nodes: HC1, HC2, HC3, HC4, HC5, HC6. And for each non-zero terms, we are going to have a node that is called as element node. Means how many element nodes you are going to have? There are 6 non-zero terms, means 6 element nodes you are going to have. And how many header nodes you are going to have? For each column 1, means 5. For 6 columns 6 header nodes, and for 5 rows 5 header nodes. Totally how many header nodes you are going to have? 5 plus 6, 11 header nodes and 6 element nodes we are going to have in the linked representation of this particular sparse matrix. Now let us see now how this can be represented. Now see here. Now this is a linked representation of the earlier sparse matrix. Now here you have 6 header nodes: 1, 2, 3, 4, 5, 6. These are the header nodes for your columns, and these are the header nodes for your rows: 1, 2, 3, 4, 5. Okay, then we need to represent all the non-zero terms in terms of element nodes. How many element nodes we are going to have? 1, 2, 3, 4, 5, 6. Now the first element node, that is for for this, in which column it is going to present? 1 2 3 4, fifth column, zeroth row. You just add that. Now in fifth column, zeroth row, we have a element node with the value 9. Its row number is 0 and its column number is 5. Likewise, you place all the element nodes at the appropriate position. Then comes the address assignments. Now first we'll see the address assignments for the header node. Now header node consists of two addresses, down and right. Now where the down of this is going to point? It is going to point at the next non-zero term in this particular column. Now the next non-zero term is this one. Okay. Similarly for this next non-zero term is this one. For this next non-zero term is this one. For this next non-zero term is this one. For this column, next non-zero term is this one. For this column, next non-zero term is this one. Okay. Now this is about header nodes downlink, and right link is going to point the next non-zero term in the same row. Now see, its right link is pointing at this row. Its right link is pointing at this node. Its right link is pointing at this node. Its right link is pointing at this node. Its right link is pointing at this. Okay, now this is how the header nodes addresses are going to be stored. Now we'll come to the element node address field. Now here you have down or up or right. Now down or up is going to contain the address of the next non-zero term. Now for this node, do you have the next non-zero term in the same column? In fifth column, 1 2 3 4. In fifth column you have only one non-zero term, that is 9. You don't have any next non-zero term. Hence this down or up link is going to point back to the header node of the same column. It is going to point back to the header node of the same column. Now come to this node. Now do you have any next non-zero term in the same column? No. Hence again it is going to point back to the header node of the same column. Now for this, do you have any next non-zero term in the same column? No. Hence it is going to point back to the header node. Now for this node, do you have any next non-zero term in the same column? No. Hence point back to the same header node. Now for this node, do you have any next non-zero term in the same column? No. Hence it is going to be come back to the header node. Now for this also same, don't have any next non-zero term, hence it is going to point back to the header node. Now why it is pointing back to the header node? It indicates that there is no next non-zero term in the same column. That for that purpose we are going to point it back to the header. Okay, now this is about the down or up link of your element node. Now the next one more address we need to assign, that is a right address. Now what this right address is going to do? It is going to contain the address of the next non-zero term in the same row. Now consider this element node. Now do you have any next non-zero term in the same row? No, you don't have any next non-zero term. Hence it is going to point back to the header node of the same row. It is going to point back to the header node of the same row. Now for this, you don't have any next non-zero term in the same row, hence it is going to point back to the header node of the same row. Now for this node, you have next non-zero term in the same row? Yes, we have. Hence it is going to point at that particular node. Now for this node, do you have any next non-zero term in the same row? No, hence it is going to point back to the header node. And then for this node, do you have any next non-zero term in the same row? No, hence it is going to point back to the same header node of the same row. For this also, don't have any next non-zero term in the same row, hence it is going to point back to the header node of the same row. Now this assignment is made to know that you have reached the end of that particular row. That's why we are assigning the right part to the header node. This is how we can represent a sparse matrix using the linked list representation. Now in this linked list representation, we are going to have two different types of nodes. Header node, the structure of header node is given by this. It consists of three components: index value, that is nothing but the row number or the column number. Down is going to point at the next non-zero term in a particular column. Right is going to point at the next non-zero number in the particular row. Then element node is going to consist of five different components or five variables. A row indicates the row number of that particular element. Column indicates the column number. Value is the value of that particular non-zero element. Down or up is going to point at the next non-zero term in the same column. If the next non-zero term is not there in the same column, it is going to point back to the header node of the same column. A right is going to point at the next non-zero term in the same row. If there is no next non-zero term in the same row, then right is going to point back to the header node of that particular row. This is how we are going to use these two types of nodes for representing a sparse matrix using a linked list. Okay, and this type of problems are going to be asked in your exams for 8 to 10 marks. They are going to specify the sparse matrix. You have to draw this chart which represents that particular sparse matrix using a linked list. Okay, this chart we need to draw using a particular sparse matrix. They are going to give the sparse matrix data. You need to draw this diagrammatic representation of linked list. How we are going to represent that sparse matrix using linked list. This diagram you need to draw. Now one more thing we can understand from this diagram. Now instead of using linked list, we are going to use a circular linked list here, because you can see here the last node of every linked list. Now here how many linked lists you have? Total linked list, can you count how many linked lists you have? Now this is one linked list, second, third, fourth, fifth, sixth, then 7, 8, 9, 10, 11, 12, 13. 13 different linked lists you have in this same sparse matrix representation. Now each linked list is made as a circular linked list because the last node is always pointing at the first node. It is again have a pointer to the first node. Hence each of these 13 linked lists are called a circular linked list because the last node of every linked list is pointing back to the first node. Hence all these are the circular linked list. Now how to count the total number of linked lists used in a sparse matrix representation? How to count it? How we can count? As I told you, there are 13 linked lists. 1, 1, 2, 3, 4, 5, 6, 7. Now there are 13 linked lists. Now this can be counted by total number of rows, total number of columns plus 2. Now the plus 2 are for one linked list for headers of your columns and one linked list for headers of your rows. Means totally how many linked lists you are going to have for a sparse matrix? Total number of rows plus total number of columns plus 2. These many of linked lists you are going to have in a sparse matrix representation. Now here in this matrix, total number of rows are 5, total number of columns are 6 plus 2. 5 plus 6 plus 2 means 13. 13 linked lists you are going to have. For why this plus 2? 1 for 1 is the header linked list for rows and 1 for the header linked list for column. These two are the additional header linked lists you are going to have in a sparse matrix representation. Okay, this is about linked list representation. Now what you do, you just see the previous question papers of the subject, and in those question papers they have asked the problems on this. They have given you the sparse matrix and you need to represent that sparse matrix using this linked list representation. You try to solve it, and if you get any difficulty you can ask. Understood how to represent a sparse matrix using linked lists? Okay, now these linked lists are circular linked lists. Okay, using circular linked lists we are going to represent a sparse matrix, and we are going to use these two types of nodes, header nodes and element nodes. Okay, try to solve the problems from the question papers. If you get any difficulty in solving, you can contact me. Okay, still if you have any doubts,